This is the final lecture in our grade 11 physics course for university preparation, and it is on acoustics. In ancient times, people would gather to watch plays and listen to music in theaters. It was as important then as it is now for people to be able to hear clearly and for the music to be of high quality. Some people say their voice has a higher quality in the shower than anywhere else. This may be true as a result of the many sound reflections that occur in a small room. Qualities of a room or auditorium that determine how well the sound is heard are called acoustics. And this is your definition for acoustics. Acoustics is the quality of sound heard in a room. It's determined by the shape and size of the room, the contents of the room, the construction materials. Without echoes, music would sound flat. The acoustics of auditoriums and theaters are designed to use echoes to ensure that everyone in the audience can hear and create the best possible sound. Here we have a person on stage. Their sound is reflecting off of sound panels at the roof of this auditorium, and it's curved in such a way that people can hear well throughout. And there's also reflective surfaces that the sound could travel. And you notice that the theater guests are seated upwards on a slant. If you've ever been to a concert, you probably noticed that when musicians stop playing, the music can still be heard for a fraction of a second. This continuation of music is due to echoes, and it is called the reverberation time. And it's usually referred to as the time it takes for sound level to drop by 60 decibels so that it's inaudible. It's a very important property in concert halls. For example, a typical graph illustrating the reverberation time in a concert hall is shown. As you can see in the graph, the sound intensity level builds up and reaches a maximum value of 70 decibels. This level is sustained briefly, and then sound is suddenly turned off at a time about 6.4 seconds. And within 1.8 seconds, the intensity levels drops from 60 decibels to 10 decibels. So that's a reverberation time of about 1.8 seconds. Why is it preferable to have short reverberation times for auditoriums where speeches are performed and longer reverberation times for auditoriums where music is performed? So it would be easier and less confusing for a person to hear a speech with a short reverberation time, and sound tends to sound better when it seems to hang around for a longer time, so you'd want a longer reverberation time for music. Reverberation time depends on the materials that are used, the height of the ceiling, the length of the hall, the presence or the absence of an audience. So these are some sound absorption coefficients for different materials. Notice that when we have a seated audience, there's a different level of absorption than when we have an empty audience with just theater seats. Number 2, Auditorium A has wooden seats and Auditorium B has cloth-covered seats. How the acoustical properties of the two theaters compare when they are empty and full. Well, when they are empty, we're going to see a difference because the cloth-covered theater seats will absorb more sound, whereas the more solid seats that are wooden would reflect that sound. When there's an audience, it won't matter so much because the people in the audience will be absorbing the sound. So it doesn't matter what the seats were made of. This is what the next two questions kind of talk about. So it's possible you can make an acoustically dead room with a reverberation time near zero. These are called anechoic rooms. They are used to study the performance of sound devices such as telephones, microphones, and loudspeakers. In this anechoic room that we have here, you can see that the walls are kind of spiked and the material actually looks like it's made of foam. What's actually happening there is the sound waves would try to reflect off of those spikes, and then they would eventually sort of reflect into the wall. And each time they reflect, they lose a little bit of energy to the material they reflect off of. So a lot of bounces means that the sound waves will deaden and be absorbed by the very soft, foamy material. When designing a room with acoustics in mind, designers try to avoid curved surfaces. When sound effects reflects off curved surfaces, it becomes either more concentrated or dispersed. But curved surfaces are used for outdoor band shells. They often have a shape of a parabola, so that with the performers being the focal point, so that the sound kind of reflects, goes from that focal point and reflects out into all places in the audience. A person standing at the center stage of this theater built 2,000 years ago could speak with an ordinary voice and be heard everywhere in the theater. Although Romans could not explain acoustics scientifically, they certainly could design theaters with excellent sound characteristics. So you can write this down for curved surfaces. There's also something called an acoustical shadow. This would be an area of a theater or a room where destructive interference would occur. It would not be some place where you'd want to have an audience members seated because it would be difficult to hear the performers in that spot. For question 3 here, it says, explain the auditorium designs in terms of the focusing of sound reflections and echoes. Which design would have better acoustics? So in A, you can see that there are some acoustical shadows. We have a lot of concentration of sound here, where we don't have a lot of concentration of sound over here. This would be better because a lot of the sound waves, the vectors of them, are reflecting down and in towards the audience. Here's a mathematical question. It says the human ear can distinguish an echo from a sound caused if the sound is separated by an interval about 0.1 seconds or more. At an air temperature of 22 degrees Celsius, what is the shortest length for an auditorium that could produce distinguishable echo or sound emanating from one end? So for this question, we are going to want to, let me move it up a little bit. We know that we're talking about an echo, so we're going to want to cut the time down from 0.10 to 0.05. We have the air temperature being calculated using this formula for the velocity of air. And in order to hear the echo, we need to determine what's the smallest possible distance. So it's D equals VT. So let's substitute in V, which is 331 plus 0.06 T times the other T. 331 plus 0.6 times 22. This is times 0.05. And let's pull up the calculator and see what we have here. 331 plus 0.6 times 22. Multiply this by 0.05. And we get 17.21, or rounding for significant digits, we have a 17-meter long auditorium.